Imagine a collision that defies intuitive physics. On one side, you have a miracle of aerospace engineering, a machine forged from titanium, carbon fiber composites, and Inconel Superalloys, designed to withstand the crushing pressures of the atmosphere and temperatures that exceed the melting point of volcanic lava. On the other side, you have a creature made of hollow bones, feathers, and soft tissue. A biological entity that weighs perhaps 4 or 5 pounds. In a static world, if you threw this creature against the side of the machine, it would bounce off harmlessly. It is soft. It is fragile. It is insignificant. But we do not live in a static world. We operate in the realm of high-velocity aerodynamics. When that machine is screaming through the troposphere at 500 miles per hour, the rules of engagement change fundamentally. The equation for kinetic energy, 1/2 mass times velocity squared, becomes the most dangerous law in the universe. The velocity is the tyrant here. Because the speed is squared in the equation, a linear increase in speed results in an exponential explosion of violence. At cruising speeds, that soft, fragile bird ceases to be an animal. It transforms into a kinetic warhead. It impacts with the concentrated energy of an artillery shell. This is the phenomenon of the bird strike. It is a chaotic, violent collision between biology and high-bypass turbofan physics, and today, we are going to freeze time to understand exactly what happens in the milliseconds after contact. Let us begin with the most critical point of impact, the intake of a modern turbofan engine. Picture the sheer scale of something like a GE9X or a Rolls-Royce Trent. The front fan is massive, often over 10 feet in diameter. These blades are not merely spinning, they are slicing through the air with a tip speed that often exceeds the speed of sound. Even when the plane is taxiing or climbing out at lower speeds, those blade tips are moving at nearly supersonic velocities. They are invisible guillotines. When a bird enters this intake, it is not sucked in by a vacuum, as is commonly believed. It is overtaken by the aircraft. The relative velocity is the key. The bird is effectively stationary, and the engine inlet is a cavernous mouth rushing forward to consume it. As the bird crosses the threshold of the intake lip, it meets the fan blades. This is the first crisis of physics. The fan blades are masterpieces of material science. In modern engines, they are often hollow titanium or composed of layered carbon fiber with a titanium leading edge. They are designed to be light, to reduce centrifugal stress, but rigid enough to compress tons of air per second. When the bird strikes the leading edge of a fan blade, the interaction is almost instantaneous. We are talking about microseconds. At impact velocities of 300 or 400 knots, the biological material of the bird does not behave like a solid. It behaves like a fluid. This is hydrodynamic impact theory. The tissues, the fluids, and the bones are compressed so rapidly that the shock wave travels through the bird's body faster than the body can mechanically deform. The bird essentially splashes against the blade, but with the density of water hitting concrete. For the fan blade, this is a catastrophic injection of energy. The titanium leading edge must slice through the mass, but the momentum of the bird imparts a massive, rearward impulse force on the blade structure. This force tries to bend the blade backward against the direction of airflow. Simultaneously, the rotation of the engine tries to rip the blade forward. The blade is caught in a violent tug-of-war. If the engineers have done their job, the blade will flex. It absorbs the kinetic energy through controlled deformation. It ripples, vibrating intensely as it dissipates the shock. But if the bird is too large, say, a Canada goose weighing 12 pounds or more, or if the impact speed is too high, the material limit is breached. The titanium snaps. Now, the scenario escalates from a biological impact to a mechanical containment event. A broken fan blade is a piece of jagged metal weighing 15 or 20 pounds, spinning at thousands of revolutions per minute. Released from the hub, it possesses enough kinetic energy to slice through the fuselage of the aircraft like a hot knife through butter. It becomes shrapnel. To prevent this nightmare, the engine casing, the nacelle surrounding the fan, is lined with layers of Kevlar or containment rings made of steel. This is the catcher's mitt. When the blade fractures, it is flung outward by centrifugal force. It slams into the casing. The casing must deform, absorb that ballistic impact, and hold the blade inside the engine. It cannot be allowed to exit the side. If it exits, it could sever hydraulic lines, puncture the fuel tanks in the wings, or depressurize the cabin. The physics of containment are brutal. The engine is essentially sacrificing itself to save the airframe. But let us assume the blades hold. Let us assume the titanium edge slices through the bird, turning a single organism into a spray of high-velocity debris. Where does that debris go? This leads us to the second circle of hell, the core ingestion. A turbofan engine is divided into two airflow paths. The bypass air, which goes around the outside of the engine core, and the core air, which goes into the compressors to be burned. If the bird strikes the outer tips of the fan, the debris is centrifugally thrown outward into the bypass duct. It exits the back of the engine as a harmless, albeit messy, spray. This is the best case scenario. However, if the bird strikes near the center of the spinner, the nose cone of the engine, the debris is sucked straight into the throat of the beast. It enters the low-pressure compressor. This is a series of smaller blades designed to pack air tighter and tighter. The tolerances here are microscopic. The gap between the spinning blades and the stationary casing is measured in thousandths of an inch. Suddenly, you introduce a chaotic mass of bone, feather, and flesh into this precision Swiss watch. The debris clogs the airflow. It bends the delicate compressor vanes. It disrupts the smooth, laminar flow of air that the engine depends on. This disruption triggers a phenomenon known as a compressor stall. In a jet engine, air must flow in one direction, front to back. It is pushed against a gradient of increasing pressure. The compressor is constantly fighting to keep the air moving backward against the natural desire of the high-pressure air to rush forward. When the bird debris disturbs the aerodynamics of the compressor blades, the blades lose their grip on the air. They stall, just like an airplane wing stalls if it climbs too steeply. When the compressor stalls, the pressure barrier collapses. The high-pressure air in the combustion chamber, the heart of the engine, suddenly has nothing holding it back. It explodes backward, rushing out the front of the engine. This is the bang that passengers hear. It is essentially a backfire of massive proportions. Flames can shoot out of the intake. The engine surges, coughing violently as it tries to re-establish the airflow. The debris continues its journey deeper, reaching the high-pressure compressor. Here, the air is being squeezed to 30 or 40 times atmospheric pressure. The temperature is rising rapidly due to thermodynamics. The biological matter is cooked instantly. It vaporizes. But the solid fragments, the bones, act like bullets. They can shatter the ceramic coatings on the turbine blades downstream. They can block the tiny cooling holes that keep the turbine blades from melting. If the debris blocks the cooling airflow, the turbine blades, which operate in an environment hotter than their own melting point, will soften and deform. The engine begins to eat itself from the inside out. The vibration sensors on the engine casing pick up the imbalance immediately. The spinning mass is now wobbling. At 10,000 RPM, a slight imbalance creates oscillating forces of thousands of pounds. This vibration shakes the entire pylon, the wing, and can be felt through the floorboards of the cabin. But the engines are not the only target. Let us shift our focus to the nose of the aircraft, the radome. This is the cone at the very front. It is not made of metal because metal would block the weather radar housed inside. Instead, it is made of fiberglass or quartz composites. It is transparent to radar waves but must be strong enough to hit a wall of air at Mach 0.85. When a large bird strikes the radome, the physics are similar to a blunt force trauma. The composite material is designed to fracture in a way that absorbs energy, preventing the bird from penetrating the pressure bulkhead behind the radome. If the bird punches through the radome, it destroys the radar antenna, a dish that is frantically sweeping back and forth to detect storms. The pilot loses their eyes for weather avoidance. The aerodynamics of the nose are ruined. The smooth airflow turns into a turbulent wake, roaring loudly and creating drag that fights the engines. Now, consider the windshield. The cockpit windows are among the most over-engineered transparencies on the planet. They are not a single pane of glass. They are a laminate sandwich. Typically, there is an outer layer of toughened glass or acrylic, a middle layer of bonding urethane or vinyl, and an inner structural layer of polycarbonate or thick glass. Between these layers, there is often a conductive film of gold or indium tin oxide. This conductive film is crucial. It carries electricity to heat the window. Why heat the window? Not just to prevent ice, but to keep the vinyl interlayer pliable. This warmth ensures that if a bird strikes the window, the layers can flex and absorb the shock rather than shattering like brittle crystal. When a bird hits the windshield, the outer layer, the sacrificial ply, often shatters. It creates a spiderweb of cracks that instantly obscures the pilot's vision. But the inner layers are designed to hold. The window bows inward, absorbing the thousands of pounds of force, and then rebounds. If the window fails, if the bird penetrates the cockpit, the result is catastrophic decompression and potential pilot incapacitation. The wind blast at 500 miles per hour enters the flight deck, creating a chaotic storm of papers, debris, and noise that makes communication impossible. Let us return to the engine, specifically the FADEC, the Full Authority Digital Engine Control. This is the brain of the engine. In the milliseconds following a bird strike, the FADEC is analyzing data from hundreds of sensors. It detects the drop in compressor pressure. It detects the spike in exhaust gas temperature. It detects the vibration. The FADEC's logic is programmed for survival. If the surge is severe, the computer may command a momentary reduction in fuel flow to allow the compressor to recover and clear the stall. It tries to burp the engine. If the vibration is too high, it might limit the maximum thrust to prevent the engine from tearing itself off the wing. All of this happens faster than the pilot can move their hand to the throttle levers. The machine is fighting to stay alive. But how do we know these systems will work? We know because engineers have spent decades perfecting the macabre art of the chicken gun. This is not a slang term, it is an industrial reality. To certify a jet engine, manufacturers must prove it can withstand a bird strike. They use a compressed air cannon, sometimes 30 or 40 feet long. They take a biological carcass, often a chicken, specifically calibrated for weight, and they fire it into a running jet engine at full takeoff power. But they don't just fire one. For the flock ingestion test, they fire multiple smaller birds simultaneously to simulate flying through a flock of starlings or geese. The engine must not only survive, it must continue to produce a specific percentage of thrust for a set duration. It must allow the pilots enough time to circle back and land. For the large bird test, they fire a single heavy projectile, for 6, sometimes 8 pounds. In this test, the engine is allowed to fail. It is allowed to quit. But it is not allowed to catch fire, and it is not allowed to release debris through the casing. It must die safely. This is the safe shutdown criterion. The violence must be contained within the nacelle. The engineering challenge is exacerbated by the trend toward fewer fan blades. Older engines had 30 or 40 narrow titanium blades. Modern engines, like those on the Dreamliner or the 777X, have fewer, wider blades made of carbon fiber. These wide-chord blades are incredibly efficient, sweeping huge volumes of air. But a wider blade presents a larger target surface. The leading edges are reinforced with titanium sheets specifically to handle the slicing action of a bird strike. The adhesion between the titanium edge and the carbon fiber body is one of the most difficult bonding challenges in materials science. If that bond fails during an impact, the titanium strip can peel off, causing an imbalance just as deadly as a broken blade. We must also consider the core lock phenomenon. If a bird strike melts the internal components or causes the casing to warp, the rotating parts may rub against the static parts. As the engine cools down during the descent, these parts can contract and seize together. The rotor locks up. This means the engine cannot windmilling, it cannot spin freely in the airflow. A windmilling engine provides hydraulic pressure and electricity to the aircraft. A locked engine is dead weight. This is why the thermal tolerance of the internal rubbing strips is so carefully calculated. The aftermath of a strike is a forensic puzzle. Maintenance crews must inspect every inch of the airflow path. They use borescopes, long, snake-like cameras, to peer deep into the compressor and turbine stages. They are looking for nicks and dents. A dent on a compressor blade might look harmless to the naked eye, but it is a stress riser. Under the cyclic loading of flight, spin up, spin down, pressurize, depressurize, that tiny dent becomes the origin point for a fatigue crack. Over time, that crack grows until the blade fails catastrophically, hundreds of flights after the bird strike occurred. This is why the sniff test is often the first diagnostic tool. The smell of burnt organic material in the bleed air system, the air used to pressurize the cabin, is a telltale sign that a bird has been processed by the core. The scale of this problem is global. Airports use falcons, noise cannons, and radar systems to keep birds away. But the sky is vast, and we are the intruders. As engines become quieter, birds are less likely to detect the approaching aircraft until it is too late. As aircraft become faster and more efficient, the energy of these collisions increases. It is a testament to the resilience of aerospace engineering that the vast majority of bird strikes result in nothing more than a logbook entry and a maintenance wash. The system absorbs the chaos. The titanium flexes, the Kevlar catches, the composites rebound, and the computer compensates. We have turned a violent collision of nature and machine into a manageable engineering variable. When you sit in a window seat and watch the wing flexing in the turbulence, remember the invisible shield of physics that surrounds you. The engines are not just generating thrust, they are armored fortresses designed to swallow projectiles and keep spinning. They are built to withstand the chaotic, messy, unpredictable reality of biological flight paths. To continue dissecting the hidden mechanics of our world, from the microscopic stress fractures to the global systems of transport, keep your focus locked on Gridonix. We do not just look at the machine, we look into the molecular violence that defines it.